Good morning, everyone, and thank you for joining us. This is Hamish Stewart from the Viavi Solutions EMEA sales team. We still have some people joining the webinar, so I'm going to wait a minute before we start. I can see that people are still coming into the webinar, so we'll just give it another 30 seconds before we start. Thanks for your patience. Okay, thanks again for waiting, everyone. So to those of you that have just joined, good morning and thank you for joining us. This is Hamish Stewart from the Viavi Solutions EMEA sales team. I want to thank you for joining our webinar today on the best practices for testing analog radios. We have a lot to share with you on the subject, but before we begin, I'd like to let you know a few things about the format that we will be following today. First of all, this webinar is being recorded and will be available for you to review or share with your colleagues in approximately 24 to 48 hours time. We will send an email to all attendees which will have a link to the recorded version. And just for your information, all lines are currently on mute, but we are monitoring the chat window and will try to answer your questions at the end of the webinar. If we're unable to do so, however, we will reach out to you individually to ensure that you get the answers you seek. And now I'd like to turn over to our speaker for today, my colleague, Barry Haig. Over to you, Barry.
Thank you, Hamish, and good morning. As I see some friends from Asia here, good afternoon and probably good evening for some of those guys. I think this is webinar number 6 that I've done. So if you've missed any other ones, please go back and review them. They are available on the Viavi website. There are other webinars that my American colleagues have done as well. So the one today we're talking about is best practices for testing analog radios. We spend a lot of time talking about digital radios and FM radios, so I've tried to focus this one on AM radios. Obviously there are FM radios and even some phase modulated radios out there. Ignoring the modulation scheme itself, the measurements and the types of measurements we do are broadly similar. Like I said, but obviously with FM or phase modulation. I'm part of a group of guys which are, shall we say, the technical experts on the radio test sets. You have myself in EMEA region. We have Mohammed in Singapore supporting the Asia Pacific region. I think he's on the call today. And 3 guys in the United States supporting the Americas, Dave, Mike, and Bill. Obviously, go to the distributor, the Viavi direct sales guy, the people in your region, and obviously for the technical side, if you need to, you can come to me if you're in EMEA. I always present this slide. I think it's quite important to show the history of Viavi in terms of the radio test sets. My history started with Marconi Instruments many years ago when I was a young baby, and they sponsored me through university. We then got it incorporated into IFR in 1998, and then Aeroflex in 2002. All of these companies were doing a lot of things with radio test. And then probably the other key acquisition into the family was in 2010 with Wiltec. So if anyone knows the German company Wiltec, or Wandel & Goltermann, Wavetech, as they used to be called, they got incorporated into the group. Then Aeroflex was purchased by Cobham in 2014, and then BIAVI purchased the test group of Aeroflex from Cobham in 2018. So this was, I think, the text that was on the invitations that went out for the webinar. Okay, so talking about AM radios with, looking avionic applications, military and private networks. Typically, they're the same sort of systems for AM. What you might find, obviously, with the military is people are using single sideband as well. And I'll just touch on that on one of the slides. But we'll look at the testing and, shall we say, programming and remote applications, automatic test applications for these types of radios. Again, the typical question, AM radio testing, why do we need to test? You're paying a lot of money for these systems. You want to make sure you've got good, reliable communications. And in many cases, just like in PMR or military, if you have an AM radio link, let's say, for example, from an airport to a control tower to a pilot, you want to make sure that communication is good and you're confident it's not going to break down just when you need to use it. What does a radio test set need to do? So we'll look at some of the measurements, and I'll talk about some of the measurement accuracy. And we've got a section in here about phase noise and why that's important, especially for AM radios. And then we'll look at automatic or semi-automatic testing of the radios as well. Okay. I've then put another slide in towards the end that just talks about novel ideas for testing radios, just to throw out some ideas of what you can do above and beyond, sitting at a bench, just testing a radio on a radio test set. This webinar is going to focus on the 3920B, but again, the 8800SX and the 3550R, in broad terms, will support similar measurements. Not all the measurements, but most of them, and I'll try and point out where there's a difference. Of course, when I talk about 3920B, that could be anything practically from the old 3901s, 02s, 3920 to 3920B. And the same for the 8800SX. It could be 8800 plain, 8800S, 8800SX. So what measurements do we want to do on an AM radio? So if we look at the transmitter, and again, you can correlate a lot of these measurements to exactly the same or similar measurements on an FM radio, or indeed, in some cases, digital radios. So we want to look at output power. Okay, so that's the first thing we'll have a look at. We want to look at frequency error. Obviously, if the radio is too far off frequency, then the receiving radio may not be able to pick up the signal. We'll look at the modulation depth. So what percentage modulation do we have, and is it correct? We'll look at the distortion, so the audio signal that we recover. We want to look at the quality of that audio signal. Another thing we might want to do, and this is more often tested, I would say, on analog radios than maybe FM or digital, is actually look at the audio bandwidth as well, especially for those ground-to-air radios. It's a test that typically is done by many of the users. And we might want a spectrum plot, just maybe to look at the modulation and how it's behaving in the spectrum, or typically we might want to do a spectral mask, or look to see if there's any unwanted signals. Could be, harmonics, could be spurious signals within our transmission. I'll show you a way where we make that easy for you as well. And as I said, harmonics and spurious, we have an application that I'll show you for those tests. Another use of the spectrometers might be if you want to, for example, set or verify the carrier suppression. So this could be where you have a suppressed carrier, for example, in the modulation scheme. On the receiver side, again, we'll look at sensitivity. So maybe we'll look for a particular SINAD or SNR value in dBs, or we'll look at a percentage distortion. You can choose any or all of those measurements. We might want to look at, again, a similar test, but here we'd be actually looking at the IF from the radio, not at the recovered audio. With the radio I have today, I don't have that capability on the radio. We might want to look at receiver selectivity or bandwidth of the receiver, and again, I'll show you how we can do that. And then other tests we might want to do, just like with FM and digital radios, we might want to check the antenna or the coupler system if we're coupling the signal into an antenna system. We might want to check the frequency response of those components, and we might want to use the tracking generator to tune filters, maybe to tune a notch or the passband, or look at duplexes, diplexes, those types of things, either for verification or tuning. Before I go into the test, there are several manufacturers that have written this into their operating and service manuals. I can't bring up any of those manuals here because of non-disclosure agreements we have with those customers, but if you have any of those manuals, and these could be for AM radios, they could actually be in aircraft maintenance manuals. But if you look in those manuals, you'll actually find reference to our products in there. And some users have actually written their own procedures around the 3920B. So here's one example. I've cut out, I think, who the customer is. So I've left it very generic for you to see. But I've worked with a number of customers who have their own procedures, especially if they're involved, again, with the ground-to-air communications, either commercial or military. So let's have a look at some measurements, and I'm going to do this just using the PowerPoint slide, and hopefully at the end, if we have a few minutes, I will show you something live on the AM radio I have here. So some of the things we might want to do is look at things like power, frequency or frequency error, the AM depth of modulation, and the AM distortion. So what I've done here, just to make it quick and easy in one essence, but also to show the quality of our generator and analyzer, I've got two modulation tones running. So I've got, just like I would with FM, I've got a 1 kilohertz audio tone, which is probably what I want to demodulate and look at in terms of the modulation quality. That's emulating the voice. But I've actually put a subaudible tone on there. And the reason I've done that, if you look at the two AM depths on the generator on the top left there, I've got 50% and 20%. Now, if you go to the analyzer on the right-hand side, in the demod section, you see the AM is measured just below 70%. So again, remember that the combined AM depth, we have a peak of 70%, which is what we measure on the AM meter. And that's quite important because just like we've talked about with FM radios and good tuning of digital radios, which generally tune using CW and FM, noise is an important factor, because with the FM deviation meter, if you add noise, or if your instrument, your test set adds noise, that will add to the FM deviation measurement. And what you see here, what I'm trying to show you with the two tones, if we had one tone and let's say the other tone was noise, you'll see that the AM depth that we measure is the peak effectively, or the sum of those AM modulation depths that I've generated. So again, any noise will add to that measurement. So we'd then get an incorrect measurement of AM depth. So again, be very careful, just like we did with FM, make sure you're using the correct IF bandwidth. Make sure if we're doing actual demod, we're actually going to look at putting some filters in here to either allow the 1 kilohertz through or the 67 hertz. Okay, then we'll actually get the AM depth for each of those different components. Okay. So in the second picture, for example, it's exactly the same modulation I'm generating, but you'll see I've now put on a sophometric filter. So think of that really as like a 300 hertz to 3.4 kilohertz voice filter. So what you see now is it's filtered out the 67 hertz, and now all I see is the 1 kilohertz tone at approximately 50% AM depth with a very good SINAD measurement, so very, very low distortion. And just as a third measurement, what I've done over here is I've showed the 67 hertz. So now I've used a 300 hertz low pass filter, and we'll see the 20% modulation depth. So you can break those tones out in a sense, depending on the filtering. Obviously, in a real world situation, those would not be two tones, they would be voice or background noise. So the other screen to look at is the bottom right of each of these traces, and you'll actually see the audio analyzer, which is an option. And that will show you the relevant levels of those three signals. Remembering in the first case on the left, I have no demodulation filter. In the middle one, I have the filter that's letting the 1 kilohertz through. And on the right-hand side, I'm letting the 67 hertz come through. So the audio analyzer can be very good. Okay, this is just a two-tone example, but in a real-world situation, you could look through there, and if there's noise or distortion, you can actually see what frequencies that is occurring at, or if it's purely just broadband noise. Obviously, if it's an aircraft, what you might find is you have you'll have a fairly high peak, which is related to the engine speed, for example. So you might find those tones easily identifiable in that audio analyzer. Next, we want to look at is the transmit audio bandwidth. This is something I did yesterday quite quickly. What I did on the generator side, okay, so in effect on a real radio, I would use the audio, the A1 audio generator that you see green, which means it's active. I would move that from 1 kilohertz, and I would sweep that value. And how I sweep that is using my mouse to click on that field of entry, the 1 kilohertz here. It would then go grey or dark grey. I could then use the left and right arrow keys to change the resolution of where I want to be, and my up and down arrow keys to shift that value. So although it's not automatic, I can basically scroll through maybe every 100 hertz. And the way I've emulated that here is I've actually changed the modulation tile above, and I fed my generator into my own analyzer as an internal loopback. So I've effectively manually swept that audio tone on the carrier, and I've put the audio analyzer on peak hold, and the red trace you see at the bottom left there, that's showing me my audio response that I've recovered, and I've put my two markers approximately around the 3 dB points. I didn't use any averaging, it's just an example, but you'll see that my 3 dB points are 330 hertz, and I think I'm up about 3.2 kilohertz from memory. If I expanded that tile, I could see the exact values. So you can actually do an audio response through the radio, through the transmitter, and you could do an equivalent response for the receiver as well, if you need to do that. Okay. Sorry, 330 hertz to effectively 2.8 kilohertz, okay, which is a little bit below the 300 hertz to 3.4 kilohertz we might expect on, shall we say, a normal FM radio. Okay. Now, if I want to look at harmonics and spurious, for example, which could be part of the spectrum measurement, okay, we have an application on here, funnily enough, called harmonics and spurious. I can set the sweep start and stop for the spurious measurements. I can set thresholds for a pass fail on spurious and thresholds for my second and third harmonics. And then what I do, I tell it to go, it will find the carrier, it will then go and find the second and third harmonics and measure those. and it will then do a spectral scan across my start-stop frequencies to look for any spurious that are, in this case, above -50 dBm, and again flag those as an error. So this is my little trusty AM portable I have here next to me, and you can see it's found the fundamental. It's found the second and third harmonics, and there are no spurious above -50 dBm, so that's good. Okay. It saves you a lot of time trying to work this out yourself and do the measurements manually. You can use that harmonic and spurious application. Okay. I didn't cover carrier suppression. We can look at that on the spectrum in a little while, for example, with the single sideband. Another important thing with the receiver test, the 3920B over the plain 3920 and the older 3901, 3902 models, the B version, effectively, the main feature there was that we improved the phase noise of the RF signal generator in the test set. So it's specified at -110 dBc per hertz at 10 kilohertz offset. And why is that important? Again, if you're trying to do measurements on AM radios, okay, some of those measurements you could get marginal passes on these types of measurements, like receiver selectivity, adjacent channel power, and adjacent channel rejection ratio. And that's because you get to the point where we sum the power in the channel bandwidth of the radio, and you get to the point where the phase noise can contribute, shall we say, a significant proportion of that. So it can in some ways compromise the measurement. So by improving that phase noise, the measurement you get now is effectively the radio and not the radio plus the test set. Okay. It doesn't mean you can't use those older test sets. It just means that you might be closer to your test limit on these measurements. So if you want a good margin, on that measurement pass-fail criteria, then the 3920B is the best unit to use. Okay, and it is one of the most important specifications of the radio test set, and it impacts AM radios probably more so than FM radios or digital radios. The digital ones are more impacted by very close in phase noise, causing jitter. So if we look at some of those receiver measurements, receiver sensitivity, for example, first of all, what I've done here is I've got 30% AM modulation tone running on my carrier. I've got a high level -50 dBm. I feed that into my radio receiver, and I look at the audio measurements. So on the right-hand side, in the top of the four windows, towards the bottom, you see it says audio, and I have some measurements in green. And remember, all the measurements that you make Okay, I hope my audio is back. For some reason, we lost the audio there, so I do apologize. I did get a warning, yes. And I did also get a phone message. Hamish, is everyone hearing me okay?
Yeah, we can hear you again okay, Barry. Thanks.
Fantastic. No idea what happened. The powers of the internet. So yeah, I was talking about receiver sensitivity here. So I just recap very quickly. On the left-hand window, I've set the power to minus 50 dBm into the radio, so a nice strong signal. I've got a 30% AM signal and a 1 kilohertz modulation tone. If I look at the analyzer window in the audio section, you see all my measurements are green. It's recovering that 1 kilohertz audio, and I have reasonable distortion. I've set my distortion limit to 5%. So in the second window, I've reduced the input level into the radio to minus 89 dBm, and my distortion is now at the pass-fail point of 5%. It's a 4.9. So I'm a dBm guy. I've used dBm. If you like dB microvolts, if you were to select that dBm box next to the generator level, you can change that to other measurements like watts, dB watts, dB microvolts, those types of things. Okay. And then what I've done on the window over here, okay, I've now got, again, a high level signal, but I've also got a high modulation depth. And you can see on this radio, that causes me significantly more distortion. Okay, and it's gone red. Okay. So that's a basic receiver sensitivity test. Excuse me. Another test we might want to do is receiver selectivity. So this is to check how good the receiver will decode our signal, maybe in the presence of other signals in neighboring channels or nearby signals. And we've made it a little bit easier for you. We have a window called the selectivity generator tile. And what that will show us in a moment is you basically set the center frequency. You then look for the upper and lower frequencies, maybe your 3 dB points, and you plug those three numbers in automatically by pushing the soft keys, and it will then tell you the total bandwidth. Well, that's quite easy. Again, that's just look at the upper and lower limits you've set or you've measured. But it also gives you the percentage of non-symmetry. And I was surprised how unsymmetrical some of these filters are on the front end of these radios. So this is how we do it. Nothing different really to how you would test receiver sensitivity, except instead of lowering the power level into the radio, we're now going to keep that constant, and we're going to move the RF frequency up and down. So here's an example, okay, with some pictures there. I'm going to jump over this and go to a real example for my radio that I did yesterday. Okay. So I'm looking again to use 5% distortion. I've put the values in here, and what you see now, you see I've moved up in frequency here. So I've gone up until I've got back to my 5% distortion, and I would press the set frequency high, and that would put that value in here. I've also put in my center frequency, and I've also put in my my lower 5% threshold here. And what you see at the bottom now, just expand that, what you see at the bottom of that window is my total bandwidth is 22.2 kilohertz. Okay, which is okay. I'm in a 25 kilohertz channel, so that's cool. But my non-symmetry is 24%. Okay, and you can see that from these two deltas. So my front end filter on my receiver effectively is not symmetrical around my center frequency of my radio. Okay, probably not too much of a big deal here, but you know, potentially you might want to retune that and make it better. Get that as close to 0% as you can. I'm not going to spend too much time on the tracking generator function. We've covered this on previous webinars, but I looked at I think a VHF antenna that I had. So I did a broadband sweep using the spectrum analyzer. So remember, if you're in the normal test window where we're showing those AM measurements and the generator and the analyzer, if you press the test button again, you get a full band spectrum analyzer. My test set goes to 2.7 gigahertz, but I've done a sweep from 10 megahertz to 1 gigahertz. And you can see that my antenna is best suited around the VHF frequencies. Actually, what I've done here, I've got two identical antennas and I've placed them close together. So if you wanted to, you could use a VSWR bridge and measure just a single antenna, or another way to do it, which is not perfect, but it's reasonable, is to have two golden antennas, okay? And then what you do, you can actually store the trace. So I've zoomed in now to the VHF band in that middle picture. So I'm now looking at 100 megahertz to 250 megahertz. And I've actually stored a trace. So I've stored the green trace. I've then recalled it. So that's my two golden antennas. I've then replaced one of those antennas with a different antenna. So I'm still using one golden antenna plus another of the same antenna, and I get the white trace. And I can look at that and say, okay, visually that's close enough, that's acceptable to me. But if you had a broken antenna, that white trace would look very different to the green one. So that's a quick way to test a lot of antennas. If you had 100 antennas, just have one set up and then just connect the second antenna as your antenna under test, and you could use this method. Okay. Another thing you might want to do is to check or tune the notch on a filter. You might want to do some tuning on some duplexers, diplexers, or something else. Okay, but there is a whole webinar that we've done already on the tracking generator capabilities. I think that focused on the 8800 SX. Again, broadly similar measurements on the 3920B. One thing to highlight is that the 8800 SX and 3550R, they do have distance to fault capability as well, which you don't get on the 3920 series. Now, my radio I've got here is a portable airband radio, airband transceiver. So it does have an emergency beacon function, or 121.5 megahertz beacon. It doesn't have the 406 megahertz satellite beacon. But if I push that, it will automatically go to that frequency and can be used as an emergency alert or as a homing beacon. What I always say to people is never test beacons using the antenna on the radio. Always a direct RF connection, or a shielded box, or a shielded room, or two or three of those combinations. I've seen emergency beacons in a screened box, especially on the 406 megahertz satellite channel. I've seen those cause an alert and helicopters get scrambled, and the radio is already in a screened box. So again, be very careful when you're playing with emergency beacons. I say the same thing if you press the red button on a digital radio these days. If it's a live network and you're trying to test the radio on a live channel, be careful with those emergency buttons. So we might want to measure just simply on that beacon. It's not a transceiver; it's just transmitting. So we might want to measure, for example, the frequency error and the transmit power. And again, make sure that IF bandwidth is wide enough to accommodate any modulation, for example, AM modulation that may be on that emergency beacon. Equally with the basic AM radios, as we narrow band now, we go from 25 kilohertz channels maybe to 12.5 kilohertz to 8.333 kilohertz. Adjust the IF bandwidth down to be most suitable. You want it wide enough to let your signals through in your channel bandwidth, but narrow enough to minimize the amount of noise. Because remember, any additive noise will add to the AM depth measurement. Okay. So in this case, we're just looking at the frequency error and the power of the radio. Just touching on single sideband, I think I've only got one slide on this. The measurements, again, are effectively broadly similar, but you cannot use a normal AM demodulator to check the measurements of single sideband. Okay. Now, 3920B or the series, 3900 series, have upper sideband, lower sideband capability, both generation and analysis. they're not available on the 8800 and 3550 series. You only have what I call plain AM on those. So here's an example. I've got a single sideband measurement, but if you look, so if you look, you can see, and this is just feeding into itself. I didn't have a single sideband radio handy when I did these measurements. If I'm trying to demodulate using AM, you'll see that my demod frequency, my AM modulation, my SINAD, they're all wrong. Okay. I think that's actually, not sure what I'm showing there. It looks almost like the same thing. But I hope over here now, what I'm showing now is the real radio. So now I'm looking at generating a single sideband, in this case upper sideband, and now I'm analyzing using the demod of upper sideband. So now you can actually see I've got a 1 kilohertz modulation, and I've got very good SINAD there of 40 dBs, and that's even without any audio filter or any demod filter there. So yeah, you might be able to do some tricks with AM to do some measurements. Obviously, you could do broadband power, get the power correct. You could use the spectrum analyzer to try and check the frequency is correct. But having that upper sideband, lower sideband demodulation capability and generation capability is very useful, especially for the military guys. But you'll also see at the center frequency, you'll see the carrier suppression. So again, we talked about that earlier. You could use the spectrum to null that carrier suppression as best you can. So I did mention at the start about some novel uses for using the radio test set. So I like to say to people, think beyond the box, think beyond the basic uses of the test set, think beyond just measuring a radio on the radio test set, because that's what you've always done. Okay, think about automating the control of the radio as well as the test set. In fact, we have a push to talk on the radio, so you could actually wire the push to talk pin on the radio test set, which is on that circular connection on the front. You could wire that into your radio, and actually, as we turn our RF generator on and off, it will turn your push to talk on and off. So if we're generating, you receive. If we're receiving, we could get you to automatically transmit. Is annual maintenance enough? I worked with a customer. Probably have to be careful what I say. It was an Air Force somewhere who had some issues with radios. So they had banks of radios, multiple channels, and the radios. Some of the radios had issues, so they were seeing some maybe unexpected behavior, and annual maintenance was not good enough, because the problem with that is the control tower or the pilot says, hey, my comms are down, and they switch to another channel. Okay, so why wait for the radio users to lose comms? Why not preemptively use your test set to just monitor all of those radios day and night, 24/7, 365 days a year? Okay, and as soon as anything starts shifting or anything goes out of spec, or you have a sudden failure, your maintenance engineers can be alerted before the control tower pilots even raise the alarm. But you may fix it before those guys even realize there's a problem. Okay, and this one, the Air Force that had this issue, they won a major award from their Air Force. They won an award for doing this work. So obviously, if you're using the test set, you could use it for 1 week every year to do your annual maintenance, but don't leave it sitting in the corner. You've paid a lot of money for the test set. Make it, use its value. Make it do some work for you. So monitor those radios, even if you do it manually once a day, once a week. Yeah, keep monitoring those radios. Is the frequency error drifting? Is the transmit power drooping because the amplifier's got very hot, it's got a bit older, and it'll droop. It'll droop over time as it warms up. Is the modulation drifting out of spec? Is the receiver sensitivity degrading? And it could be degrading because of interference. So again, monitor for interference. I know some of the things we found in the UK. We've had air traffic systems go down or be compromised because of LED security lighting. Yes, they switch to LED lighting around remote radio sites. An animal walks past at night, the spotlights come on, it triggers an alarm, and the receiver gets compromised because of the broadband noise you get from these in some cases poor quality LED lighting inverters. LED light bulbs at home also cause a similar problem. So if anyone's having problems around dusk, they suddenly see problems happening in the evening and at night that don't happen in the daytime, it could well be LED light bulbs. Moving on to remote control and test scripts. Again, we've done this in another seminar, another webinar, but I want to touch on it. So I've stolen some of the slides from the other webinar and I've added, I think, an extra one or two. But why would you want to automate some of these tests or procedures? Okay. If you're in a radio workshop, for example, and you have multiple test sets and multiple radio types, a lot of radio throughput, make it more efficient, speed it up. Okay, you can sort of de-skill the process. You don't de-skill fixing the radios or necessarily tuning them, but in terms of testing, you can de-skill that and speed it up. Okay. If you're running the same radio types, but lots and lots of those radios, tens, hundreds a day or a week, again, automate some of that testing. Tests that take a lot of manual button pushing, receiver sensitivity, you keep lowering the power level until you hit an SNR, a cyanide, or a distortion value. Again, automate those types of functions. Same with the duplex testing, same with that receiver selectivity or bandwidth checks. Also with the audio bandwidth, again, automate those types of tests. Save yourself a lot of time. And in terms of spectrum and interference hunting or monitoring, again, just have the test set reporting. You could be reporting broadband power, you could be grabbing spectrum traces over time. All of this is there for you to use, and let us know if you're not sure how to do this. We'll help you. So on the 3920B, we can have test scripts built in. Some are fully automatic, where we control the radio and the test set, and it will do a complete test, both transmit and receive, and in fact, it will do alignment in most cases. Or they'll be semi-automatic, where you may have to have a bit of user intervention or operator intervention. Turn the knob to position 3, key the radio, look on the display, what is the value? So all of this will speed things up. Some of those are written by ourselves and approved by the radio OEMs. Some are written by the OEMs, and some are written by the end users. So here's an example of one test for an AM radio, for an airband radio, for example, which is fully automatic and built into the test set. Okay, and here's an example for the 8800, where I've taken a radio similar to the one I have here, and I've written a script using Python. So I'm controlling the 8800 SX via Ethernet and a Python script on my Windows laptop, and it's getting the TX measurements and RX measurements. And all it tells me to do is turn the radio to channel 1, key the radio, and dekey the radio. That's it. So the one on the left, fully automatic with control of the radio. The one on the right, semi-automatic with 3 user interventions. Okay. So if you're running remote applications, you can use the remote control commands to do an automatic program, or you can use VNC software. So in this case, use type VNC typically. I can look at my 3920B screen on my laptop remotely. I can be in the same room like I am today. I can be on a corporate network. I can be on the internet anywhere in the world. So as long as I can get through the firewall to that test set, I have capability to look at it. Same with 8800 SX 3550R. One difference here is 3550R and 8800 SX, only one person can connect at a time, only one VNC connection. On the 3920 series, you can have up to 10 people connected. Okay. Can make it difficult if more than one person's trying to control the mouse. But you could have multiple sites monitoring, or multiple people, especially if you're working at home now, could be monitoring a test set at a radio site or an airport or at an industrial plant, looking for interference or issues with the radios. And you don't have to be there. You can be sitting at home, in a nice comfortable chair, TV in the background. So doesn't have to be fully automatic. You can just do manual work like this. Remember, it's bi-directional control. You can control the test set remotely, or someone can control the test set and you can see it on your remote screen. Okay, I've mentioned Python. Just in this example, again, you've I think already seen this. It was for portable AM radios and vehicle mount AM radios at an airport, and they needed this to get safety approval. It was part of the safety approval for the air show that they held. Okay, and to test one channel on that radio, both transmit and receive, took 20 seconds. So the setup of the test set and doing the measurements took about 20 seconds. Okay, easily put that in a loop and make it do multiple channels if that's what you wanted. Another example was looking at rack-mounted, shall we say, ground-to-air radios. When we're actually controlling the radio, if you look at that middle picture, we're actually sending a lot of RS-232 commands, which we can do from the test set, to a telecoms test set, which is basically the control interface into that ground-to-air radio. Okay, so not only are we controlling the test set, we're controlling a third-party piece of equipment and doing all the measurements on the radio. I think to finish up on this, just another test script. This is one that I wrote on the 3920 for a customer. And I have complete control of the radio. I can even ask it what its firmware version is, even the temperature of the power amplifier. And then I can do transmitter and receiver measurements automatically. In this case, it's one channel. I could do it on 100 channels if I wanted. But to do the setup, grab control of the radio, take all the parameters out of the radio in terms of firmware, etc. Do the transmitter and receiver measurements on one channel, 28 seconds. Again, much quicker than you could do yourself. Okay, and I've done something equivalent for that radio using Python. So USB to serial control of the radio and Ethernet control of the radio test set itself. So I've almost finished. Many users still use their trusty old analog radio test sets, and there's nothing wrong with those. I see people who just don't want to give them up, and in some cases that's absolutely right. Why should you? Here's a selection of some of those that I see out in the field. I was a Marconi guy working on signal generators when my friends were developing the 2945 all those years ago. Probably shows my age. Obviously, the more modern ones, we have things like the 2948B, also IFR being part of our family with the COM 120B, the Wiltec Stabilox, 4032s, 4016s, those types of products. And then the old HP products and the old Rohde & Schwarz products. Many of these are still working, still being used, but they're getting harder to maintain, harder to service and support. And remember, just like with the digital radios, tuning them, we realized that these older radio test sets actually generate a lot more internal IF and RF noise, shall we say, that can impact those FM deviation measurements when we tune the digital radios. And the conclusion from that is it will also impact those AM depth measurements. So if you want more accuracy on those AM depth measurements, you need to use the more modern, what I call digital radio test sets. Okay. And here's just one example that we had a customer wanted, and this is a major national, shall we say, civil aviation authority somewhere in the world. May not be in Europe, but they had selected many years ago the 2945B with some options. Okay, so 4 options there. And the equivalent on the 3920B is just the base unit, okay, plus the warranty in the transit case. So all of those extras you had to buy on the old analog test set are standard features on the newer test set. Okay. So in summary, AM radio testing has some requirements beyond analog, FM, and digital. Again, think about the quality of the AM depth measurement, and if that's really important to you, in which case you've got to think about using the correct IF filters and reducing the noise that's added by the test set, which includes phase noise plus other broadband noise. That's broadly equivalent to the white paper we did for the digital radio tuning. Good quality measurements are essential. Again, if we're switching different IF filters, for example, or audio filters, our filters are digital now, they're flat, perfectly flat. In the 2945 as a good example, the filters were real, resistors and capacitors. So when you switch those filters, you had any uncertainty in the switch if the contacts were aged or not very clean, and also tolerances in the components. So again, the filters these days are all software, they're perfect, as opposed to the old days where they were a few % out because of tolerances on the components. Okay, and remember, it's very, very important we stress this, that the AM depth measurement is impacted by any noise. So optimize the IF bandwidth, the IF filter. Okay, the spectrum analyzer and tracking generator capabilities add useful additional functions and features like tuning filters and checking antennas and monitoring for interference, those types of things. Highly recommend you consider test applications, whether they come from us or yourselves or a third party, to automate things, save you time, save you effort, and save you money. And we've got just over 5 minutes to go, I think. So I'll throw it back to Hamish with any questions that have come in. And any questions we don't get to, we will reply to you via email. But I can also bring up my live test set.
Yep. Okay.
So
thank you very
for
much
listening so far.
Yeah, and thank you very much for that great presentation, Barry. And apologies to everyone for the issues that we had with audio. Hopefully we didn't miss out too much. So we have quite a lot of questions. I doubt that we will get through them in the remaining 5 minutes that we have. So we'll answer as many as we can, and any that we can't answer, we will include those in the package that goes out to you after the webinar when we send out the recording. So the first question, Barry, and I think you may have covered this in the presentation. Is there a possibility to add cable loss into the test set in any way when you're performing the measurements?
Well, I'm hoping that's come from somebody who has a 3920B. That's a really good question and something I should have picked up on. Absolutely, you definitely need to use cable loss, and I'd missed it out, and I deliberately did it because I was going to bring it up and I forgot. So I'm really pleased someone's asked that question. Whenever I do radio seminars or live radio workshops, I quite often see people haven't used cable losses, and I don't care if it's AM, FM, or digital. Does it really matter? Well, if your cable loss is half a dB, yeah, okay, so your generator, your sensitivity is out by half a dB. But if it's half a dB in its power, then it can become more significant. Or if it's, you've got a longer cable, 1, 2, 3 dBs, if it's a 3 dB cable, which you hope you wouldn't have at VHF, but maybe at UHF you could. If I'm trying to generate 10 watts, a perfect radio, if I had a 3 dB loss, I would measure 5 watts. And then I'd retune the radio back up to 10 watts. Now, in fact, it's really producing 20 watts. So it is very, very important. And if I may, let me turn off my generator and actually turn on my real radio. Okay. So hopefully that's going to settle down. It's about 1.5 watts. But as you say, I don't have any cable loss in there. Okay. So under config, one of the things I have, there's a lot of things I can do is offset. So let's, my cable I think is about 0.3 at VHF, but let's say it's, Anyone see what I did wrong there? I made it positive, so it was gain. I don't have an amplifier. Oops. So I've got to switch them on here and here. Okay. So my 1.5 watts has gone up to 1.66 watts. Okay. But if that was 1 dB or 2 dBs for the cable, that incorrect power that I had would be very significant. Okay. And what you'll see in some places, you'll see plus or minus signs. So here I've got a generator offset, here I've got an analyzer offset. So very good question. Thank you very much.
Okay, thank you for that, Barry. So the next question we have is, will these tests work with any AM transceiver or receiver, or will they just work with airband ones?
No, I've used airband as an example because that's where a lot of the AM radios are used these days. The military use them, but a lot of all commercial aviation use them. And in terms of AM radios, I have an airband radio. I also have a military radio that has AM and single sideband and other modulations. But I've used my commercial radio, which is an airband radio. So that's why I focus a lot on airband. A, because that's what I've got here. But secondly, that's where a lot of people have a lot of interest in making sure those radios are working as well as they can because of the safety critical situations they're in. You know, if your DMR or FM walkie-talkies don't work in a factory, you know, you might pick up your cell phone or you might go and talk to someone on a landline or walk over to them. If you're 39,000 feet in the air and your radio doesn't work, you know, you've got some issues. Sure, there's other systems available, but you really want those voice channels working correctly. So yes, any AM radio, you could do these measurements.
Okay, thank you, Barry. So the next question relates to the phase noise performance that you mentioned on the 3920B. And the question is, does the 8800 SX have the same phase noise performance? And if not, what are the consequences of using this for taking measurements on radios?
Okay, so if you look at if I start with the 3900, the 3901, 3902, 3920 plane without the B on the end, the 8800 series and the 3550 series, they all have broadly similar performance. It's only 3920B that has the improved performance. So that is the one that is typically chosen, for example, by the civil aviation authorities, by the militaries. As I said, if you use the what I call the classical performance, i.e. the 8800 or the 3920 plane model, for most commercial people with who are not doing the very high-end radios with very good performance, yeah, typically you still have good measurements, okay, but you're getting close to compromising some of those measurements. Like I said, selectivity would be one example. The reason it's more critical in the higher end applications is, you know, if you're using AM radios to talk over a 10-mile range, not a big deal. If you're trying to talk over several hundred miles, you know, to an aircraft that's out across, you know, the Pacific Ocean or the Atlantic Ocean, then, you know, you want to have comms as good as you can get it, as much range as you can get. So it can be more important, some of those radios. Okay.
Okay, so we're approaching our 10 a.m. cutoff here in the UK. So unfortunately, I don't think we're going to get through all of the rest of the questions, but maybe we can just squeeze one last question in. Maybe one of the easier ones that would be quicker to answer is, can I use the test set to work on FM and DMR radios too?
Yeah, of course. I mean, the standard they have AM and FM. The digital systems on all the test sets tend to be options. So yeah, you can, obviously I've talked about AM today, but previously I've talked about FM systems and DMR, you know, Tetra type systems. So yeah, depending what options you have on the test set, you can do other radio systems as well. You're not limited to AM or just AM and FM.
Okay, all right. Well, thank you for that, Barry. And as I said, that we do have an extensive list of questions here. Unfortunately, we don't have the time on the webinar today to answer them all, but we will get answers out to each and every one of you that have asked questions, and we will respond to you via email, and we will get the list of questions out to everyone along with the webinar recording. So thank you once again, Barry, and thanks to you all for joining the webinar today. If you think of any more questions or would like further information, please reach out to either myself or Barry with your questions and requests for information. And please join us on our next webinar, which is going to be run on the 19th of August. And that will be about testing FM radios and FSK modems. So you can go to the Viavi webinars page to register for that, and we would look forward to seeing you then. So thanks again, everyone, and have a good day. Bye-bye.
Thank you, everyone. Bye-bye.